this is a joint work with a PhD student of mine at the University of Iowa, Jingwen Tian, who is in the audience right now. This is a very simple project, something that took off from a very simple observation. We essentially have in mind a new industry. So it's a typical patent licensing situation, but with some important small modifications that will lead to different results. Typically, it would be more appropriate to think of this as product innovation. So the innovation that's going to get licensed is a product innovation rather than process innovation. But you can also think of process innovation if you think of it as something quite drastic defined in a slightly different way than usual. So we would think here of a drastic process innovation as one in which if a single firm produces with a new technology, then all other firms would have to be out of the market. So to just fix ideas and be clearer, let's just think of a new product innovation. So basically, even better, a new industry. And the only way a firm can enter this industry is to buy the patent from a lab. And the innovator throughout the talk will be a lab. So that's the basic situation. And we're going to think about profit sharing. So a fixed share of profit will go from the licensee to the licensor. But on top of it, that aspect is also different from the usual situation. In the usual situation, we have an existing market structure. We're given the number of firms and we think about an endogenous licensing mode, say a share of profit or share of revenue to be paid from the licensee to the licensor. Here, we should rather think of a fixed profit sharing proportion and an endogenous market structure. So what the licensor chooses, or what the lab chooses is how many firms it will sell the innovation to, and these firms would then be allowed to operate on the market. All other firms will be excluded in the basic model. I'll be talking about some modifications of the basic model where there may be existing firms in the industry that produce and already have a technology that allows them to produce. But that's a modification. So back to the basic model, there's one lab and an endogenous number of firms to be determined by the lab. And the decision variable at the hands of the lab is not the profit sharing rate. That will be assumed exogenous and fixed by historical considerations or by existing practice in neighboring industries. Rather, the decision variable will be how many firms to sell the innovation to. So in this sense, then, compared to the usual situation, the lab determines perfectly the market structure. Because of these modifications, it turns out that the setup is very close to the basic results and model from the theory of divisionalization. So for those of you who don't know that theory, since we have a somewhat heterogeneous audience, I will summarize the basic results from divisionalization theory. So briefly, here is, I guess, we're talking about profit sharing licensing. It's, as we saw in several talks in this workshop, it's a rather recent strand in this literature. And otherwise, we have a priori the basic classic model. The classic models usually consider fixed number of firms N. And usually we have a monopoly patent holder in the classical models, licensing. In this paper, we do as well in the first model, but then a key aspect of what I'll talk about today is that we introduce possible competition among labs. So if two or more labs at the same time come up with the same innovation that would allow a licensee to enter or licensees to enter the industry, then the labs would compete amongst themselves. So a paper that looks at this in the past is our, I don't even know how to, oh yeah, okay. Is Aurora and Phosphori, but they don't go into any of the aspects I'll be talking about. So here's the, so the industry can be a new industry. That's the easiest thing to think about to fix idea, or one with pre-existing firms. There are 4 different models. The basic ones are new industries, but some of them will have pre-existing firms. And the pre-existing firms will be assumed to just want to produce, and they're not involved in the licensing possibilities or discussions. And other potential entrants are simply excluded by technological barriers. If you don't have this technology, you simply cannot produce the good that defines this industry, and you simply cannot enter. All right, so here are the 4 scenarios. The basic model, the simplest to describe, is one lab in a new industry. New industry means no incumbents. All entrants are licensees, and they have to purchase the innovation from the lab to enter. The lab is not a producer. Then we go to one lab with a pre-existing industry. Pre-existing industry means there are few incumbents to start with. The third model is there are more than one lab, at least 2 labs, no existing firms. And the last one is multiple labs in a pre-existing industry. So the key assumption is this: the profit sharing rate is not endogenous, it's exogenously determined according to historical practice in related industries. Could be, it doesn't matter what it is, as long as it's exogenous and fixed. Could be 10%, 20%, 50%, 80%, whatever, as long as it's constant. When we go from one lab to multiple labs, this constant could change. So it could be 10%, no, sorry, it could be 60% when it's a monopoly lab, and 20% when it's a duopolistic labs, as long as you keep these proportions fixed for each market structure. Market structure in the lab, the higher end of the market among labs. Instead, labs compete in the quantity of licensees. So each lab gets to pick how many firms, so there are potentially many firms, and each lab picks how many firms it wishes to sell the license to. And therefore, we can think of each lab, if a lab decides to pick 2 firms to sell to, then it's a bit like creating 2 divisions in the endogenous divisionalization game of, say, Corchon and Bayat al in this literature. So I'll be talking about, so the strategic divisionalization is the opposite of mergers. You have a kernel model and 2 firms merge. Pradeep, do you have a question?
Yeah, something has gone wrong.
I'm hearing, sorry, I'm not
Can
hearing
you hear me?
because there's background noise.
Yeah, I don't know why.
I think there are 2 Zoom connections are open. You have to close one.
I see. Okay.
Otherwise, there will be feedback. Yeah.
Can you hear me?
Yes.
Now I can hear you. Yes.
Yes, now better. Yes.
Okay. Question is, are the labs producing the same homogeneous product substitutes, or are they producing different qualities?
So in this paper, the product is homogeneous, but actually a more appropriate model will have differentiated products. So it doesn't matter whether basically the 2, if there are 2 labs, then what the technology they sell or the product they sell will be homogeneous.
Okay.
Yeah, but that's simplification. You will see later that it's better if we had allowed heterogeneous products, differentiated products. And for each of the 4 versions of the model, we wish to answer the questions of what market structure will emerge as the subgame perfect equilibrium. So the game we have in mind is in the first stage, each lab decides how many firms to sell the license to. And in the second stage, all the licensees compete in a Cournot model with linear demand, linear costs, the usual simple setup. I'll talk about general demand towards the end of it. So here's the setting, usual linear inverse demand. Yeah, here's the stage one. If we have one lab, then the lab determines how many firms to license to. If there are two labs, then each one determines how many firms to license to. For each firm that is chosen as a licensee, there's a fixed cost for that firm to actually enter and operate in the industry. You can think of the fixed cost as being to purchase equipment, or in particular to have training costs. This F could be zero. In some of the remarks I'll make, this F would be zero, but generally it's a positive fixed cost. It's a fixed cost, it's per firm. So each firm would have to pay this cost. If it decides to buy a license, it has to pay for the license as a percentage of its profit, of its anticipated profit, and it will pay a fixed cost to operate in the industry. And at stage two, after all the entrants have been observed, they compete in standard full information Cournot with constant marginal cost C, and the lab gets this proportion theta that is exogenous as a share of the profit of each firm. All right.
So here it's just an entry cost to enter the game, right?
Yes. So if you wish to enter this new industry, you can think of minoxidil, the only product that the medical profession recognizes as having some effect in allowing hair to regrow for balding people. Then there's a lab that has this technology. You have to buy it from them to enter. And you have to go through a training that costs something to be able to.
Otherwise, Rabah, you get infinite, you don't get an equilibrium, and whatever you do, I do one more.
That's right. You see it here. You saw it exactly. So that's the story.
You know that there is a paper that I wrote with two guys from Stony Brook, appeared in 2020, very similar to that, competing innovators. And you have many firms. That's exactly, very, very similar to that one. But you should just look at it. It appeared in Mathematical Social Science by Badia, Bruno Badia and Billig to Remendebal.
Okay. So it's similar to this setup?
Pardon me?
It's similar.
No, but
to this
we have even dynamic that you can go. And then you look on the steady state. It's a little bit more. With dynamics in it, time and stuff. But we had the same problem. We call it training cost or something like that.
All right. So let's talk about it later on. See if
Yeah.
Basically, I think you're seeing where this thing goes. Once you have the setup, it's kind of obvious what the results will be. Sorry.
A quick clarification. So when you say fixed fee, it is just for, you are saying that it's a fee that you have to pay upfront, or it's a cost that one has to bear for get trained, or
It's
so,
not so there are two things. One is profit sharing. You pay theta share of your profit.
Okay.
So let's say you pay 10% of your profit to the lab. And the other thing is you pay a fixed cost F to learn how to operate this technology, and which is not production cost. Production cost is a constant unit cost C. This is a fixed cost to kind of enter. It's a fixed cost to enter the industry that has to be incurred. It doesn't go to the lab. It just is incurred.
Doesn't go to the lab. Exactly. That's my point. It doesn't go to the lab.
Yeah.
Okay.
Yeah,
okay. All right. Okay.
All right. So the setup is linear demand, linear production costs, and actually we call K this fixed cost that we just talked about. This training cost, K per firm. So firm I chooses the number of independent divisions Ni, and then all divisions compete à la Cournot in stage 2. So if we look, this is the basic model. So along a subgang perfect equilibrium, the payoff of firm I is this, where this fraction is just the Cournot profits if you have this many firms competing, small ni plus capital N minus I. So this is how many firms compete à la Cournot. This is the usual expression for per firm Cournot profits. And since, this should be lab I. Yeah, this should be lab I.
May I have a question?
Yeah.
You're considering the case of only one lab?
Yeah, so I'm describing the case, the basic model I'm describing as if you had several labs.
Oh, okay.
And then later we say that, in the first model there's one lab, but in later models there are several labs. So this is the profit function as a function of the number of firms picked by lab I. So this should be lab I picks Ni. This is the Cournot profit function for each firm that's been picked and enters the industry. And the total number of firms is just little Ni, what lab I picked, plus this variable, which is the sum of the total of all firms picked by all other labs than I. Okay? And then minus K times Ni, because for each firm you pick for each firm that lab I picks to enter the industry, there's a fixed cost K. And so let me just say the result, and then I'll come back to analyzing this payoff function. So the key results are that if K is, I guess maybe let me just go to, oh my God, I think I have the wrong, okay, I have the wrong slides, but it doesn't matter. I don't know how I did this. Okay.
It looks like it's not matching what you said in the previous slide, the notations. Yeah, here you've got. Go ahead. So I'm just trying to understand the payoff of this is one of the firms who buy the license from the lab.
This is the payoff actually of the lab.
Oh, payoff of the lab.
Right.
There's one lab.
Each lab. So the lab I'm looking at, lab I, picks Ni, little Ni. This is the total number of firms picked by all the labs.
Okay.
And this is Cournot profits when you have this many firms competing. Right? So each lab is picking little Ni. This is the total number of firms picked. So each firm will have this ratio as its profit, equilibrium Cournot profit. And since lab I picks little Ni firms, this is the total revenue of lab I. And each firm has to pay cost K to operate. So you have to subtract the total. So this altogether, this is the payoff of lab I.
What is the cost?
Cournot equilibrium in stage 2.
What is the cost of the lab? Why that is coming there? What is the cost of the lab?
Because not the cost of the lab. This is the total cost. It's the total fixed cost of allowing Ni firms to enter.
Okay.
It's the cost for the lab to train Ni firms to operate in this industry.
Okay.
K per firm. But you pick Ni firms, so the total is K times Ni.
You have to train them. Okay, I see. So that's the cost. Okay.
Something like that, or or some.
Okay.
So they have to buy equipment So if K is 0, this is Yair's comment a little earlier, then it's known. You can just take the first order condition. The reaction curve of lab I is this one. So the optimal number of firms chosen by lab I in response to this many firm capital N sub minus 1 by all other labs is just to pick how this just comes from the first order condition of this payoff. It's however many firms are picked by all others, you add 1. And this is if there's no fixed cost. And therefore, the reaction curve is a line parallel to the diagonal, but above the diagonal. So if you, let's say if you have 2 firms, these 2 lines only intersect at infinity. So at the pure strategy Nash equilibrium in the NIs, you have infinitely many firms. Each NI is infinite. So that's why, as Yair said, this is why we need to have this fixed cost if we don't want infinitely many firms and perfect competition. But it's also realistic to have positive K. So actually, let me just say a note about the literature. This comes directly from the divisionalization literature, the Korchon papers, for instance. And he didn't have this K, he had set K equals 0, so he got infinitely many firms, and he says the divisionalization game leads to perfect competition. So in most of the talk today, I will assume K positive, as in the paper by Bay et al. In AER 96. And then this reaction curve reduces to something that's actually increasing and then decreasing. And there's unique equilibrium, and it has finitely many firms. Obviously, how many firms it has depends on A, B, C, etc., and K. So I don't give the formula because it's somewhat complicated, but it's very easy to solve. And another result of this literature on divisionalization is if M is equal to 2, so you know the M is, remember, M is the number of labs. So here to the end standing is, I'm basically reviewing the divisionalization literature where these are mother firms. But in our model with licensing, a mother firm is just a lab. So if there were 2 labs to start with, then the sub-game perfect equilibrium of this game actually coincides with the second best socially optimal number of firms. Okay, so this is a result directly from the divisionalization literature from Bay et al., AER 96. They show that this divisionalization game, when you start with 2 mother firms and they pick how many divisions to have each, they end up at the sub-game perfect Nash equilibrium, which is unique. They end up picking the second best socially optimal number of firms. This is perhaps a good time to ask questions, if any. So again, this slide is really the divisionalization model, but if you just replace M firms with M labs, then it's also tells you exactly what would happen in our licensing game if the licensing rate is fixed, theta, it's 10%, let's say, or 60%, whatever it is, but it's fixed. And the decision variable of the firms is, of the labs, is how many firms each of them would pick. Any clarifications so far?
Just one little one. So M is the number of firms, and there is 1 lab, right?
No, sorry, I described the situation. So this is the divisionalization game. The M mother firms, so let's forget licensing now. Divisionalization. The M mother firms, and each one decides how many independent subsidiaries it will have.
Okay.
And that this slides describe exactly the outcome of this game. This is just the divisionalization literature. These are not our results. This is, again, Korchon and Bay et al. This is precisely Bay et, this is all in Bay et al. So now we come in and say, take out the word M firms here and write M labs, since each lab picks the number of firms it wishes to allow in and takes a fixed proportion of their profits. The model is isomorphic to this model, and we get the same type of equilibrium.
Okay.
So that's the situation. So now let me go to the actual licensing setup. and resolve this. So theta is a fixed, this is the equilibrium profit per firm when n firms are competing. So now I'm looking at the situation where we have a single,
What is puzzling is if this is a license, then you still take theta and f as exogenously fixed parameters.
yeah, so the theta
Whereas
doesn't matter
normally
here because again,
in
it's a fixed proportion of the.
I know, whereas in the past, the theta, which was like R, and F, which was the fixed cost, were strategic variables of the
Exactly.
lab. Now you are taking out those strategic variables and only
That's right.
putting the number of licenses. Yes.
So that's the trick. So we fix the rate at which the licensee extracts profits from the licensor extract profits from the licensees, but we vary the number of licensees.
Earlier, you were varying all three, and in the previous papers, not in your paper, N, theta, and F were all three were announced by the innovator.
No, F was exogenous. F is just how much training cost you need.
Okay, in your model.
Yeah, F is, as throughout the talk, this F is just the cost for each firm to enter this industry and operate. For instance, training costs. So in the usual divisionization story, this theta is just one because the total profits.
But yeah, Rabah, you have changed the story. Now it's not a firm and divisions. It's a lab selling the license to the firms.
That's right.
The lab could set F strategically, but
no. So this F is fixed.
I understand.
The N, that the only strategic variable here is N.
Okay.
You pick how many firms you wish to sell the technologies to, thereby allowing them to enter this industry, but you cannot remove the fact that they need to pay the F to operate each.
You said they need to pay, actually it is borne by the lab, right? This fixed cost? Is it borne by the lab or the firm?
It's borne by the lab.
So borne by the lab, exactly. So it is not
pays it and,
yes,
and charges a theta sufficiently large to cover it.
Yeah, so it is not like a fixed fee, or the fixed fee is basically it goes to the innovator. In this case, innovator pays to train the particular firm to be part of that lab.
That's right. So what the lab gets is exactly what's written here.
Yeah.
Theta times the total profit of the number of firms it allows in. The N times the per firm profit. So, I mean, in some sense, no, I guess I take it back. It's the firms that pay the F.
Oh, yeah, that is confusing. Whether the firm is paying or the lab is paying, that part is...
The firm is paying because otherwise you should,
Who is paying the training cost?
Sorry, I didn't answer correctly. So it is each firm's profit is this, minus the fixed cost that it pays, and then the lab takes proportion theta out loud.
Yes, exactly.
Who is collecting the fixed costs in the model? Nobody.
The fixed costs are collected by some industry
here outside the model.
These services.
Yeah, okay.
So think of the F as the the firm has to send some engineers to be trained, and that's their travel cost.
Yeah, it doesn't come to the lab. It doesn't come to the lab.
It doesn't go to the lab, no. Yeah. And so if you have one lab, then obviously N star is equal to 1. And the reason is just that monopoly is the market structure that maximizes industry profit. And so if you have one lab and no existing firms to start with, the lab would pick a single firm to sell to because it knows that monopoly maximizes the profit of any industry with linear costs. And so it will sell to a single firm and collect 10% of the monopoly profits. So this is a very simple observation that if we start with a single lab and no existing firms in the industry, we get monopoly.
Mhm.
So licensing in this style for no industry product innovation leads to monopoly directly. Now we're going to make the model a little more complicated. We're going to assume that there are existing firms already in this industry, and the lab does not have to sell them anything, cannot sell them anything. The lab can decide how many new firms to sell to. But we know that suppose F is 0 now. If F is 0, we know the reaction function of the lab is just this. We can think of this n sub minus I as being the number of existing firms. The lab will just, if there's no fixed cost, this condition, the lab will take the number of existing firms and just add 1 to them. Okay, so if there were 2 firms to start with, they for some reason had the technology already operating in that industry, the lab would pick 3 extra firms. There were 2, the lab would pick 3, so we have a total of 5. This is if there's no fixed cost. But if there's a fixed cost, then the lab would pick less than, strictly less than 3. Maybe 3 if the fixed cost is tiny, but more likely 2 or 1. Okay? And they would just add up the number of firms picked by the lab would add up to the existing firms, and that determines the market structure. So that's the next, okay. So yeah, let's little bit background again. Let me just go to the paper of Mankiw and Winston on second best socially optimal entry. This is the welfare function of a Cournot model. This is the area under the inverse demand curve up to the total output. This is the total Cournot output minus C times the total Cournot output minus the total entry costs. This is, sorry for the different notation, but I guess in the usual Cournot model, the fixed cost of entry is F. So this F is our K. And as in Mankiw and Winston, when demand is linear and costs are linear, production costs are linear, this is the socially optimal number of firms. So the result here is we get a monopoly out of if there's a single lab and it's a new industry, we get monopoly. I'm just repeating that. And if there are M incumbent firms, then the lab would pick M plus 1 new firms if there's no fixed cost. And if there's a fixed cost, I didn't write down the expression because it's messy, but again, it would pick some number between the existing number, which is M incumbent firms. So it would pick M plus not 1, less than that, but at most M plus 1. And the intuition is that when the lab gives a license to 1 more firm, it faces a trade-off, which is that adding 1 more firm increases the licensee's market share against the incumbents, against, in this case, the existing firms. But the per firm profit decreases because you intensify competition by adding 1 more firm. So this is, again, just the direct intuition from divisionalization. So in terms of what is the result, again, to summarize? If you have M existing firms, and supposing K is 0, the entry cost, then the lab would sell to M plus 1 firms, yielding a total of 2 M plus 1 firms in that industry. But because K is typically positive, there is a fixed cost for each firm to operate, each new firm to operate, then the total number of firms in the end will be strictly less than 2M plus 1. So it will be between M, the existing number, and 2M plus 1. And actually the total number of licenses, this is the first order condition for what it is. And it's easy to show that there's a unique solution, but it's not possible to give a closed form solution for it because this is a cubic equation. And the licensing game may lead to the second best socially optimal number of firms if and only if the socially optimal number of firm according to the Menke-Winston welfare maximization formula is equal to the existing number of firms plus the number that's picked by the lab. All right, so this is the situation of a new industry, a single lab, existing firms in the industry equal to M. Now we go to the next model, which is there are L labs, but we have a new industry. So no incumbents in the industry and L labs competing. So these L labs are assumed to have developed the same technology that allows entry to any firms, to any number of firms that purchases the license from any one of the labs. And then the payoff function of any lab is this, where theta is the fixed profit sharing rate. Again, it doesn't matter what it is. It could be different from the situation with one lab, as long as it's fixed and not a decision variable. The decision variable of lab I is Ni, and this is the profit function of each firm when this lab picks N sub I and all other labs pick N sub minus I. And yeah, you subtract. So the same as before, basically. And this is the first order condition for how many labs will be picked as a unique symmetric subgame perfect equilibrium, and the solution N tilde is the solution to this cubic equation. And the result is that the solution N tilde, which is the subgame perfect symmetric Nash equilibrium, in that equilibrium, the licensing game exactly leads to the socially optimal number of firms, which comes from maximizing welfare according to Menke and Winston, as I showed a few slides back.
So by the way, you mean it's a unique subgame perfect equilibrium and it happens to also be symmetric?
That's right, yes. That's right, yeah, good clarification. I don't mean that there may be asymmetric ones.
Yes,
There's a unique one and it is symmetric.
Okay.
So then we recover the result from the divisionalization literature that with K positive, it so happens that this very non-cooperative game in the end leads to a second best socially optimal number of firms. By the way, in some sense, the result also holds if K is 0 without any fixed cost to enter the industry, we get perfect competition as we saw, and perfect competition in that case without fixed cost is also socially optimal. So in the end, the result really holds for independently of the value of K, including the value K equals 0. All right.
The fraction theta, so that is on the net profit, not, so it's on the profit net of F.
Sorry, I didn't hear you.
The fraction theta, the sharing, that is on the profit net of the setup cost F.
That's right. So this is the profit. The theta is a share of the profit of each firm net of the entry cost.
And that's why your results don't depend on theta, because if it is on the gross profit, maybe they will depend on theta.
You mean if I put this F outside of the bracket?
That's right, yes.
Would they depend on theta? Yes, then that basically means the fixed cost is directly paid by the lab. Yeah, then that's right. Yeah, they would depend. Yes. All right. So the last model has L labs, just like the previous model, but it also has N incumbents. In other words, before these labs made this discovery, this innovation, there were already M firms that were operating in the industry, and those incumbents are not selling anything, they're just producing and continuing to produce, and the L labs have to strategically decide how many new firms each to sell licenses to. So the problem is a little more complicated because this M comes into the objective function of each lab, but still it's very easy to analyze the subgame equilibrium, and the result is that the socially optimal number of labs is at most 2. So we have examples where it is 2, we have examples where it is 1, but it's never 3 or higher than 3. So the basic conclusion is once you introduce competition amongst labs in this particular way, then you don't need that much competition. With already 2 labs, you get the second best socially optimal number of firms, and any more labs, if they happen to be around or if there's a policy to create them, would actually be counterproductive. If labs extract payment from licensees in the special way described in this model. So I would say this is the takeaway. If you have a single innovator and no existing firms, you actually get a very extreme market structure. That's the first model. You get monopoly. As soon as you have 2 labs and no incumbents, you get the socially optimal number of firms. And when you add incumbents to either model, either monopoly lab or duopoly lab, they actually change the results. And in the case of monopoly, they change it in some sense dramatically, because again, if you have 2 incumbent firms, because of the lab selling this innovation, you get 5 firms in the end. 2 plus 2 plus 1, so that's 5. So there's a drastic effect of having incumbents. Even if you have a single incumbent and an innovating lab, you end up with 3 firms in that industry. But increasing competition at the sort of upstream on the labs, on the number of labs, is only useful as you move from 1 to 2 labs, and from there on, there's no point in increasing competition. If this is the variable for society, it's better to just increase it from 1 to 2 and stop there. So that's basically it. Thank you. And I'm happy to take questions and reactions. Obviously, this is the perfect audience to present this work to. This has not been presented before. Slides were literally written a couple of days ago. And Yair, I'd like to hear from you if you have, again, if you had a paper that shares some common features with this one.
Yeah, I mean, the paper that we have is about, I mean, we face the same difficulty. So we went to an infinite, not repeated. I mean, you have countable many periods, and in every period, you have 2 innovators of the same, I mean, similar innovation. And every period you decide if you want to delay. Why should I delay? Maybe I see how many you license, then I would license maybe 1 more or whatever. And so every period we simultaneously decide delay or license. But once we license, we don't change. There's a like contractual that we accumulate every period the amount of that they pay me, all of my licensees, but it continues forever. And there is a discount factor, delta, and what we show actually.
I know this paper, yeah. I handled your paper.
Oh, really?
Yes.
So you should remember that. And then you have the equilibrium is a mixed strategy. I mean, there is a unique stationary subgame perfect equilibrium, and which is a mixed strategy equilibrium. But then with some probability, what's nice that you don't necessarily license in the first period. It may be on the 10th period.
Right.
And it's a probability one and stuff like this. But we encounter, why we did it, because we encountered the same problem as you, to go to infinity and stuff like this. So we wanted to take another approach a little bit. But
in
it's
the
good.
end,
Okay.
so I remember the paper, but not so much now that we worked on this paper, which is very recent.
So
But your paper, in some sense, is more complicated.
yeah, it is a
And
little bit
doesn't
more
really
complicated.
get the same results.
Even though it's 6 pages in the, or 6 or 7 pages in the journal. I just sent it to you, okay?
Okay.
For your convenience. So look on it. It's obviously you do different, a little bit different, and both are interesting.
I have a slightly question of clarification. So when there are incumbent firms, Rabah, they already are producing the product. The labs are selling the same product to new entrants.
They're selling technology to allow the new entrants to
come
join
in, but that technology already exists with the incumbents.
Yes, so that's right. So we have to tell a story there to.
Because if it's a real innovation, it doesn't exist yet in anywhere.
Right. So we have to tell a
you
story
have some
as to
other
why.
story in mind. What's that story?
Yeah. So we have to tell justification as to why this
Something
happens.
is existing.
Again, that's one reason why I said earlier that having differentiated products is more interesting. So, for instance, it could be that the incumbents sell a brown good, and that brown good is discontinued. No one is allowed to, because of environmental reasons, no one is allowed to produce it going forward. But if you have a green version of it, then you're allowed to produce. And what the labs sell is the green version, the green technology for it.
Okay.
For instance.
My opinion is that
but then the
your contribution is not very different from the literature of divisionalization.
Ramon, you're completely right. That's why I said in the beginning, it's a very simple model. It's just a way to build a bridge between divisionalization and licensing. And for some reason, except in the paper by Yair that I have to look at again. So for some reasons, these very simple remarks have not been made before. And I'm somewhat surprised that no one has, at least as far as we know, no one has made these observations before. You're one of the people who has contributed to divisionalization, right?
To mergers more than divisionalization, but
I'm sorry?
To mergers more than divisionalization.
Yeah, I know mergers for sure. Mergers,
but it's the same thing.
Well, but you even have a paper on divisionalization, I thought. You have lots of papers on
yes,
mergers,
yes, yes.